so far in the text, you've encountered a number of physical vectors, and you've seen a set of objects called geometric vectors, which we use as a mathematical model. Now, what we're going to do now is to make a start on building up a mathematical structure of vectors. And as a first step in this, we're going to introduce an addition operation called vector addition. So, how do we define the addition of two vectors? Well, we shall want a definition that is going to be useful to us. That is, it must model the way in which physical vectors are found to combine with one another. And the clue here lies in the problem we asked you to do before watching the program. If you remember the problem, you wanted to fly from Exeter, down here, up to Edinburgh. But there was no direct flight, so you had to fly first to Belfast and then up to Edinburgh. Well, let's think about this in terms of the displacement vectors that are involved. Firstly, you have the displacement from Exeter up to Belfast, and then the displacement from Belfast to Edinburgh. And as far as displacements are concerned, the net effect of these two is the same as a single displacement from Exeter up to Edinburgh, just like that. Now, we can interpret this by saying that these two vectors here add to give this third displacement vector here. And there's a vector addition rule. We call it the triangle addition rule. So to add any two vectors, you place them like these two, tail to head, and you put in the resultant from the tail of the first up to the head of the second. So there's a vector addition rule, but it does depend on the way displacements add. And as you know, there are other kinds of physical vectors. How do they add? Do they add by the same method?
Geometric vectors turn out to be useful in other situations too, but you always have to check that the triangle rule carries over. Now imagine, if you will, this situation where we have a river flowing, a drake on the far side of the river, and a bevy of ducks over here, and they're all trying to get across the river to the drake. So the first one sets out heading straight for the drake, like this. But she forgot to allow for the current of the river, so she didn't quite make it. The second one tries again, and this time she sets off pointing upriver. And again, didn't get straight to the drake. Now, the drake has the pick of the whole flock of ducks, and so he decides that he will only have the duck which can swim straight to him. Well, amongst the ducks, there's one with a mathematical turn of mind, and that's what we're interested in really too, the mathematics. So let's see if we can work out what she has to do. What she knows about the situation is, first of all, that the river's flowing like this, in this direction, so that's a good starter for a geometric vector. It's got magnitude and direction. Then, the duck knows the direction that the drake is in. It's a direction like this. And thirdly, she knows how fast she can paddle. So let's see if we can do something about finding out what direction she needs to go in. Now, we know that the direction of the river and the speed is a vector, something like this. We know the direction in which she has to finally paddle is something like that. And the first duck set off actually in that direction. So she was adding her velocity to the river's velocity like this, and it's not surprising that she didn't get to the drake. What our duck has to do is to try and fit in her velocity so that it comes over here, something like that, and makes a resultant velocity in the correct direction. So let's see if we can draw that. Now, the speed of the river is like that. Here's the direction that the duck needs to go in. And here is the length of the duck's velocity. The first one set off like this. Our duck needs to set off in a direction that will take her along that resultant. Now let's measure that angle. Here it is, like that. I'll take that back over to the river and see how she gets on. Not bad for a duck. And now we've seen that velocities add using the triangle rule too.
So the triangle rule that we got from displacements works with velocities too. And now, what about forces? Forces have magnitude and direction. How do forces add? Well, take a look at this setup here. You can see two forces acting on the ring here. One force along this string direction, the other force along that string direction. The force magnitudes are given by the weights here that hang on the other ends of the pulley. Now, there's also a third force acting on that ring. It's the force provided by the peg here that holds it steady. Could you determine what the force of the peg is? What's its magnitude and direction? Well, let's have a look. Let's assume that the two forces in the strings here can be added by the triangle rule. Well, we know their directions and we know their magnitudes. That means that we could draw geometric vectors, do a triangle addition, and find their resultant. But how would that help us? Well, it helps us because the peg is providing a balancing force. A balancing force equal in magnitude to that of the resultant of these two, but opposite in direction. So let's do that. Let's find that resultant. Well, I'm going to have some geometric vectors here, and perhaps, Anne, if you'll help me with some television magic. We need a geometric vector 8 units long to represent the longer of the two forces, and I see it's there already. And the other one has to be 6 units long. That's it, in the direction of the string. And now to add them by triangle addition, we have to move the longer until its tail is sitting on the head of the shorter of the two. And if you could now put the resultant in from the tail of the first, the head of the second. There's the resultant. Now, that resultant is 9 units long. I know that because I measured it before the program. I know from that the magnitude and direction of the resultant. Here's a force of 9 units provided by these weights here. And what I'm going to do is I'm going to apply this force to the ring. And I'm going to align its direction so that this force is opposite in direction to the resultant that we had on there. It's a matter of aligning the string direction. There it is, equal in magnitude and opposite in direction. Now, if we're right about this, then this third force is doing the job that the peg was doing, balancing the resultant. So if I take the peg out, the ring should remain held steady. So there we are, we don't need the peg anymore. So we started off by assuming that these two forces add by triangle addition. And things worked out. So I think that's pretty good evidence that forces do add by the triangle addition law. So now, let's have a look at another situation where vectors are adding.
There's another important area where geometric vectors turn out to be important, and it's really quite surprising. It's this situation. When something's spinning, how would you model that spin by a geometric vector? Well, let's look at it in more detail. Here's a disk that's spinning, and it's this spin that we want to model with a geometric vector. We need a length or a magnitude. That's not too bad, that's the angular speed. But what about a direction? Well, using the clock rule, this is spinning in a clockwise direction from where I'm looking at it, so it'll be a vector in that direction, like this. Now here it is again. A spin like that. Clockwise from where I'm looking at it, so it's a vector pointing away from me. Now I can arrange for this ball to spin in several different ways. Another way is like this. And that spin is a vector in this direction. What will happen if I turn on both motors at once, combining the two spins? Now that spin is clockwise from below, so it's a vector pointing upwards. Now let's see if the triangle addition rule will give us that kind of result. The first thing to do is to move this vector so that it's adding onto the end of this one, like that. And the result then of this vector and that one is here. Indeed, a vector pointing upwards. Well, let's put that away just now and try a slightly different situation. I can switch this switch so that it rotates the ball like this. And that's a spin represented by this vector. Now again, if I switch this one like this, that's that vector. Now I want to see if I can use the triangle addition rule to predict what happens when I have both of these two together. Well, the first step is to move this arrow down here like that. And then the result is this vector going from here to here. That is a spin like this. So it works. And spin too can be represented by a geometric vector, and that adds using the triangle addition rule.
So let's see what we've got so far. You know that vectors are quantities that have a direction, a magnitude, and you've seen in the program that vectors add by the triangle addition rule. But at this stage, we really ought to develop our model, because so far we've added our vectors using geometric vectors drawn on a page. And it's not always convenient to draw geometric vectors. have a look at this practical problem here. What I've got here is a mock-up of a sailing dinghy. The mast here is being held in a vertical position by the 3 stays here. The forces in the stays are parallel to the length of the stays, and their magnitudes can be read off on the spring balance down here. So the situation we have is that there are 3 forces here acting on the mast. And it's important from the design point of view to know what the resultant force on the mast is, because it's acting in a downwards direction on the hull. And the hull has to be designed strong enough to support that force. So how could we predict the resultant of these 3 forces acting on the mast? Well, I don't think we could draw geometric vectors here, because the 3 forces are acting in 3 dimensions. It's not convenient to draw. So what we need is a new model of vectors. We need a numerical model.
What we need to be able to handle 3-dimensional vectors is to be able to calculate with them. And to do that, let's go back to 2 dimensions. Here's a vector C, and I can break it up into 2 parts. A part in the x direction and a part in the y direction by using the triangle rule backwards. Now, this vector A I can think of as being a scaling of a unit vector, a vector of unit length in the x direction, which is denoted by I, and then A is just A times this vector I, and the vector B, again, can be thought of as a scaling in the y direction by taking B times J, a vector of unit length in the y direction. That is, my vector C can be written as A lots of I plus B lots of J. And you can do this with any vector. Let's now have a look at another one. I'll take this vector D, which is 4 lots of I and 2 lots of J, like that, and then add to it the vector E, which is 3 lots of I and 8 lots of J. That's 3, 8. If I add those together, then I've got 1, 2, 3, 4, 5, 6, 7 I plus 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 J. That's this vector. And by putting that in there, you can see that all I've done here is to add the i's and add the j's. So to add vectors, all we need to do is to add together the x components and the y components.
So, components of a vector. That's the idea I need here. Let's see how it works in 3 dimensions. Well, I've got a vector in 3-dimensional space here. Also, I've got a set of 3 axes. You see, x-axis along here, y-axis, and up here is the z-axis. 3 axes for 3 dimensions. Now let me put on the components of that vector. Here's the x component along the x-axis. And now let me put in the y component. Here it is. So there we have both the x and y components, but we're not finished yet because there's the z component to put in yet. Well, here it is. So there are the three components of my vector. And we could write this down numerically like this. Vector R is the sum of its three components. Here's the x component of magnitude x, the number x, and I gives its direction along the x-axis. Here's the y component, and here's the z component of length z units, and in the direction k, which we're using as the unit vector along the z-axis. And of course, to add any two such vectors, we simply add the corresponding components. So how does that help us with our problem here? See, we have our three forces here acting on the mast. The magnitudes of the forces we can read off on the spring balances down here. For example, this one is 14 units. That one is 14 units as well. And this one at the front here is 8 units. Well, I've got geometric vectors here cut to length, and I can put them in position so that you can see these forces acting on the mast. That one of 14 units length, and this one over here, right at the back of the mast, is also 14 units of length. And then the one at the front, well, that one was 8 units. And these three forces here can be added by adding their corresponding components. But of course, before I can talk about components, I need coordinate axes. So let's put in some axes. Let's have the x and y axes horizontal on the deck of the boat. Then the z-axis can be vertical. You can think of the mast as being the z-axis. Now, if we're just interested in the vertical downward component of the forces, after all, that's the force that's acting downward on the hull, then we need to concentrate only on the z components of these three forces. Let me put them in. First, this one, acting down the z-axis like that. Its length, you can get its length easily enough. You know that that's 8 units of length, and it's just 8 times the cosine of the angle between these two. That's just trigonometry, and that gives the length of this z component. And of course, we can do the same for the other components, and I'll place them like this, head to tail, so that you can see how they add. And you can see that they give quite a substantial force acting downwards on the hull. So perhaps you can begin to see the designer's problem there. Also, I hope you can begin to see just how useful this idea of vector components can be. In fact, it's one of the most important ideas in this unit.